All right, in this video, we're going to talk about subspaces of Rn. So in previous videos, we talked about what it means for a subset of Rn to be closed under vector addition and what it means to be closed under scalar multiplication. And if you have a set that does both of those things, that has both of those properties, it's called a subspace. So the definition of a subspace is this. A subset or a subspace W of Rn, so it's a subset of Rn, it's a non-empty subset. Okay, what does non-empty subset mean? So there's something called the empty set. The empty set is the set that consists of no elements. And what it means to be a non-empty subset is that there has to be at least one element in W. So W has to have at least one vector in it, is what it means. So a non-empty subset of Rn that is closed under, for the purpose of this series of lectures, don't worry about the empty set. Okay, it's not really a big deal. So that's closed under addition, that's vector addition, and scalar multiplication. And is closed under scalar multiplication. So let's look at an example. Remember, a subset is literally just a collection of vectors in Rn, just any collection of vectors in Rn. Okay, it could be a finite collection of vectors in Rn, it could be an infinite. I mean, it doesn't have to have any pattern or anything whatsoever. It's just literally any collection of vectors in Rn is a subset. But the subspace is a special type of subset. It's a subset that satisfies the closure under addition property and the closure under scalar multiplication property. So let's look at an example. Let's say that W is the set of vectors xy such that y is equal to negative 3x. Now this, it turns out, is a subspace of R, well, it's a subset of R2, and it's a subspace, turns out, to be a subspace of R2. Now, why is this true? We have to back this assertion up. So what does W look like anyway? W, so you have y equals negative 3x, it's this line. Okay, it's supposed to go through the origin, and W is all the vectors on this line, right? W consists of all the vectors on this line that goes through the origin. That's W. So why is this a subspace? First of all, we need to show that it's non-empty. Well, it's non-empty because, say, 0, 0 is in W. How do we know 0, 0 is in W? Because 0 is equal to negative 3 times 0. Remember, this is part of the skills that you're learning when you're learning linear algebra, is reading this notation. What this is saying, when you have something like this, it's saying, so my notation is that x is the first component, y is the second component. So this is saying that it's all the vectors where the second component is negative 3 times the first component. And when you look at the vector 0, 0, is the second component negative 3 times the first component? Well, yes, because 0 is equal to negative 3 times 0. Okay, so W is a non-empty set. That's good. There's actually vectors that satisfy the equation. And now the next thing we need is closure under addition, which means that whenever you add two vectors in W, the result is also in W. And since W consists of infinitely many vectors, right, it's not possible to literally add all the possible vectors in W together and check that they're all in W, because you have an infinite number of vectors in W. So let's say that V1 is a vector in W, and V2 is a vector in W. And I'm using x1, y1, and x2, y2 as the components. So let these be vectors in W. So what you want to show is we want to show that V1 plus V2, the sum, is in W. And now we need to practice writing out what it means for a vector to be in W, right? What distinguishes a vector that's in W from a vector that's not? What makes a vector in W? What makes a vector in W is that the second component is -3 times the first component. That's what needs to happen in order for a vector to be in W. So we know, since V1 is in W, that since V1 is an element of W, and I'm using this notation, we need to get used to this notation, this mathematical notation. Since V1 is in W, Y1 is equal to -3x1, and since V2 is an element of W, Y2 is equal to -3x2. Now what we need to show is that V1 plus V2 is in W. Well, okay, well first let's figure out what V1 plus V2 actually is. So we have V1 plus V2 is, you add the components x1 plus x2, y1 plus y2. What do you need to know in order to show that this vector is in W? We need to show that the second component is -3 times the first component. That's what a vector has to do in order to be in W. So we need to show that the second component, y1 plus y2, is equal to -3 times the first component. Well, we know that y1 is equal to -3x1 and y2 is -3x2. So can we get this equation from those two? Yes, right? Because we can pull out the -3 from the sum. So we know, so we have y1 plus y2 is equal to -3x1 plus -3x2. That's equal to -3x1 minus 3x. I didn't even need to do that. I could just already pull out the sum. I could pull out the -3 out here already. So this is going to be -3 times x1 plus x2. And what that shows is that V1 plus V2 is in fact in W. Thus, W is closed under vector addition. That's how you write a proof that the set is closed under addition. And now the next thing we need to show, this is the last thing, is we need to check closure under scalar multiplication. So what we need to do is we need to show that whenever you have a vector in W in any scalar, that scalar multiple is also an element of W. So let's say that you have a vector v, which is xy. Let this be a vector in W, and let c be a real number. We need to show that CV is an element of W. And again, we need to write out what it means. We have a vector v in W. So since v is in W, we know that the second component y is negative 3 times the first component. And we have CV, this vector is just Cx, Cy. Now what do we want to show about Cx and Cy? What do we need to know about those components to know that CV is an element of W? We need to know that the second component is equal to negative 3 times the first component. So we need to check that the second component is negative 3 times the first component. Well, we have that y is equal to negative 3x. Since y is equal to negative 3x, we know that what can we do? What can we do to get from this equation to that equation? We can multiply both sides by c. So we get cy is c times negative 3x, and that's the same as negative 3 times cx. So that shows that CV is an element of W. And since V was arbitrary and C was arbitrary, this shows that whenever you take a vector in W, any scalar multiple has to be in W. That means that W is closed under scalar multiplication. And so we showed that W is a non-empty set. It's closed under addition and closed under scalar multiplication. So therefore, W is, in fact, a subspace, okay, of R2. So that whole explanation that we did, all of this is the proof that W is a subspace of R2. And in general, whenever you have a line in R2 that goes through the origin, that's a subspace of R2. So in general, a line in R2 that passes through the origin (0, 0) is a subspace of R2 by the same sort of reasoning. Okay. Now what happens if you have a line that doesn't go through the origin? So let's look at an example. Let's say that you have the set of vectors x, y again, this is in R2, such that y is equal to x plus 1. So the question is this a subspace of R2? So to be not a subspace means either it's the empty set. Well, is W the empty set? No, right? For instance, the vector 0, 1 is an element of W. So W is not empty, but if it's not closed under addition or not closed under scalar multiplication, then it's not a subspace. So let's see if W is closed under addition. What do you think? Well, the answer is no, it's not closed under, let's show that W is not closed under addition. Okay, so what we need to do is we need to find two vectors in W where the sum is not in W. Well, we can try something like 0, 1. 0, 1 is an element of W because 1 is in fact 0 plus 1. And can you come up with another vector in W? How about 1, 2? That's in W because the second component is 1 more than the first component. But if you add them, what do you get? You get 1, 3. And that is definitely not in W, which is not in W. Okay. Which is not in W because the first component, 3, is not equal to 1 plus the second component. So that shows that W is not closed under vector addition. You're able to take two vectors in W, and by adding, you're able to get outside W by adding vectors. That's, if you're a subspace, you're not allowed to do that. You have to stay within W. And I'll let you check that W also isn't closed under scalar multiplication either. That's an aside. I mean, since W is not closed under addition, it's certainly not a subspace, right? Subspace means it has to do all three things. It has to be non-empty and closed under vector addition and closed under scalar multiplication. Well, if you're not closed under addition, okay, that's already one of the things. You only need one of the things to not happen, and then you're automatically not a subspace. I mean, subspace needs to do, all three things need to hold, okay? But I'll let you check that W isn't closed under scalar multiplication either. Okay, even though we didn't need to know that in order to know that W is not a subspace. So let's take a look at the picture. So if you look at the line y equals x plus 1, that's going to look like, well, it has slope 1 and goes through 0, 1. Now I wanted to go over this example because there is a common misconception. And the common misconception is, see, a lot of people will look at this and say, well, this is a subspace. And this is what they're going to say. They're going to say something like, well, because, okay, let's say you take a vector like this. That's like, right, like this. And then you take another vector like this. Well, when you add them, you're gonna get like a vector like this, and it stays along the line. So the set is closed under vector addition. And it's also closed under scalar multiplication because if you take a vector on this line and then scale it, you sort of stay on the same line. So people will say, well, it's also closed under scalar multiplication. Now that is wrong. It's not closed under vector addition, and it's not closed under scalar multiplication. This is not the right picture. Okay, this is not the right picture. The right picture, the way you should think about this is you have a line like this, and the vectors are like this. Okay, like this is a vector v1 on the line, and then, you know, you have something like this, which is a vector v2 on the line, and when you add them, you get this vector v3. This is v1 plus v2, and this vector is most definitely not on the blue line. Remember what it means to say that a vector is on the line. Okay, what does it mean to say that this vector is in W, where W is quote unquote this line? What it means is that when you draw a vector that starts at the origin and goes out, okay, to the end, that point at the end is on the line. So this vector v1 is in W because the tip of the vector is on the line, and the same thing for v2, right? But v3, the sum, the tip is not on the line, so v3 is not an element of W. Okay, that's the picture you want to have. Okay, because we're talking about, adding vectors and stuff like that, we're identifying the vectors with the corresponding points. So for instance, like 0, 1 needs to be, in order to identify this point, this vector 0, 1 with the point 0, 1, you need to actually have your arrow start from the origin and end up and make the tip of the arrow match the actual point that you're talking about. Okay. So we see that this is the correct picture, and in fact, when you have this particular V1 and V2, the sum is not in W. And it's the same thing with scalar multiplication. So the correct picture is you have something like V1 like this, and then when you scale, when you take like 3 times that, you're going to get this, and then this point is not on the blue line. Okay, so this is, okay, maybe more like 2.5 V1, right? It's this vector. That's not on the line. And yeah, and so in general, whenever you have a line in R2 that does not go through the origin, a line in R2 that does not go through the origin is never a subspace. In fact, it's not closed. It's never closed under vector addition, and it's never closed under scalar multiplication. Okay. So it's kind of interesting because whenever you have a line through the origin, it passes all 3 properties. It's non-empty. Non-empty is not such a big deal, honestly. But it's non-empty. It closed under vector addition and is closed under scalar multiplication. But as soon as you have a line that doesn't go through the origin, it doesn't have any of those properties. It doesn't have any of the closure properties. All right. This says scalar. And actually, whenever you have a subspace, it must contain the 0 vector. So all subspaces W of Rn must contain the 0 vector. So that's a fact. It's not a very complicated fact. It's okay, it's not hard to explain why it's true. The reason is because we know that W is non-empty, so it contains some vector. And let's call that vector V. Well, by the closure under, so since W is closed under scalar multiplication, okay, any scalar multiple of V must be in W. Well, what if you take your scalar to be 0? Since W is closed under scalar multiplication, 0 times V must be in W. But what's 0 times V? That's the 0 vector. So the 0 vector must be in W. So that's actually another quick reason to see that this set W is not a subspace, because 0, 0 is not an element of W. But just because a subspace contains the 0 vector, that doesn't mean that just because it contains the 0 vector, that it's automatically a subspace, right? So warning, a set that contains the zero vector isn't necessarily a subspace. We actually saw examples of that if you look at the videos on closure under addition and scalar multiplication. So if you took, for instance, this set S, which consists of all x and y such that x and y are greater than or equal to 0, right? So S is the set of x and y such that x and y are both greater than or equal to 0. This contains 0, 0 because 0 is greater than or equal to 0. So S contains the origin, but now is this set closed under scalar, is it closed under vector addition? What do you think? The answer is yes. If you have two vectors, v1 and v2, and the components of those vectors are all greater than or equal to 0, then when you add them, the result, the components will also be greater than or equal to 0. The kicker is that S is not closed under scalar multiplication. So to explain why this is true, so let's just say, to justify this, for example, we need to come up with a specific V in S and a C such that CV is not an S. Well, let's say you take V to be, say, 1, 1. So this is in S because, just in case it's not clear, 1 is greater than or equal to 0. But if you take -1 times V, that's going to be -1, -1, and that is not an element of S because x and y in this case are not greater than or equal to 0 because -1 is less than 0. So that shows that S is not closed under scalar multiplication. Okay, let's look at some other examples. Well, actually, Rn is a subspace of Rn. Because it contains the zero vector, and whenever you add two vectors in Rn, you get something in Rn, and when you take a vector and you scale it, you also get a vector in Rn. Okay, I'm not going to write out a proof of that. I mean, that's just from the definition of Rn, basically. And, okay, that's one example. And also the zero vector, the set consisting of the zero vector is a subspace of Rn. Okay, why is that true? Well, this set is non-empty because it contains the zero vector, and it's closed under addition because the only two vectors in this set are 0, and the sum is the zero vector, and that is in the set. And when you have closure under scalar multiplication, well, the only vector that's in the set is the zero vector, and whenever you take a scalar multiple of that, you get the zero vector. So that might be a good idea to write this out, the details of this yourself, to check that you understand this. Okay. And one more thing to know is that, let's go back to the definition. So this is another perspective, another point of view on subspaces. So let's say that W is a subspace of Rn. if W is a subspace of Rn, and it contains V1 and V2, then it must contain C1 V1 and C2 V2 for any scalars C1 and C2. So scalars being real numbers. That's because W is closed under scalar multiplication. And therefore, so C1 V1 is in W and C2 V2 is in W. Now, since W is closed under addition, so W must contain, it has to contain the sum, right? It has to contain C1 V1 plus C2 V2. In other words, what this shows is that W, i.e., W contains all linear combinations of vectors in W. Whenever you have two vectors in W and take any linear combination, that also must be in W. And also, if W has this property, then W must be closed under addition and closed under scalar multiplication. So let's just isolate this as a property. If V1 and V2 are in W, then W contains every linear combination of V1 and V2. Now let's look at this property by itself. Let's say that W is a subset that satisfies this property. If W is any subset of Rn that satisfies this property, star, okay, that whenever W contains two vectors, it must contain every linear combination, then W must be a subspace of Rn. Because V1 plus V2 and CV1 are linear combinations of V1 and V2. So the point I'm trying to make is that we can also define a subspace to be any set that satisfies this property, star. So the conclusion is we can also define a subspace to be any subset W that satisfies star. So the benefit of that, of thinking about a subspace like this, is that you only have to check kind of one criterion instead of three criterions. I mean, the non-empty thing is not really an issue because in all the examples, W will be a non-empty set. So it's really two criteria. But instead of checking closure under vector addition separately from closure under scalar multiplication, which is what we did here, you can simplify what you have to check to this one criterion. Okay. And so we can use that to come up with another example of a subspace. So this is an important example. So let's say that A is any matrix. Before, we haven't talked about matrices and subspaces. Now we're taking a matrix and looking at the subspaces associated with the matrix. Then the set of solutions, the solution set of the equation Ax equals 0 is a subspace of Rn. Okay. So in other words, we're looking at all the x's such that A times x is the 0 vector. And one thing we can do is we can check that it contains the 0 vector, it's non-empty, okay? And we can check that it's closed under scalar multiplication and check that it's closed under vector addition. But first we can check that it's non-empty. So let's say we call this W. So the 0 vector is an element of W because A times the 0 vector is the 0 vector. Okay. And we need to check, the next criterion is closure under linear combinations. See, that's one criterion. So we would say let V1 and V2 be in W, and let C1 and C2 be real numbers. We want to show that C1 V1 plus C2 V2 is an element of W. Well, again, we have to use the definition of W. It's all the vectors that A maps to 0. So we have, since V1 and V2 are in W, we have A times V1 is the 0 vector, and A times V2 is the 0 vector. Now keep in mind that this 0 vector we're talking about is the 0 vector in Rm, right? Because the outputs are in Rm. Okay. So what do we need to check? We need to check that this vector is in W. What does that mean? It means that A times that vector is the 0 vector. So let's multiply A by this vector. Well, now we can use the linearity property of matrix vector multiplication. This is C1 times AV1 plus C2 times AV2. And now do you see what we can do? We have AV1 is 0, AV2 is 0. So this is going to be C1 times the 0 vector plus C2 times the 0 vector, and that's the 0 vector. Therefore, okay, what did we do? We showed that this linear combination gets mapped to 0 by A, gets mapped to the 0 vector by A. So therefore C1 V1 plus C2 V2 is an element of W, so W is a subspace of Rn. It is a subset of Rn, and we show that it's a subspace. Okay. So notice how much easier that is. I mean, it's sort of you take closure under scalar multiplication and closure under addition and sort of combine it into one criterion. All right, we'll talk more about subspaces next time. This was a pretty long video because of all the proofs. But even though the definition of subspace is fairly abstract, it's a set that satisfies some properties. It turns out that we have a very concrete way of thinking about subspaces of Rn. They turn out to just be what you get when you take a bunch of vectors and you look at the span. The span of a set of vectors is a subspace, and every subspace of Rn is a span of a finite set of vectors. We'll talk about that next time. Thanks.